However, I don't need to tell you that language models like GPT-3 and GPT-4 are already far more powerful than earlier language models. Just as cars, mobile phones, and computers have continued to improve, language models have continued to improve since their inception. In this talk, we will talk about the history of language model evolution and the main points of natural language processing. I know that most colleagues will not do this work, but understanding the development trend of natural language processing and the limitations of current methods can help us rationally view chat and eliminate superstition about artificial intelligence. Phase 1. The first stage of language model development was before the 1990s, when Ulinek et al. Used it to solve the problem of automatic speech recognition. Prior to this, computers could only recognize more than 100 English words, and the recognition error rate was still very high. After using algorithms in communication and introducing language models, IBM's automatic speech recognition system can recognize 22,000 English words, and the error rate has dropped from about 30% in the past to less than 10%. What does this mean? When the error rate of recognition is controlled within 10%, that is, less than one word is wrong for every 10 words recognized, it will have application value. Because at this time, people can correct that one typo based on their own knowledge. This matter, a young man at that time touched a lot. He is still in Carnegie Mellon University PhD Lee Kai-Fu. After obtaining the consent of his mentor, Kai-Fu Lee decided to abandon the traditional artificial intelligence path taken by Carnegie Mellon University and use IBM's method to achieve a practical automatic speech recognition system. Later, he did it, and became a rising star in the US at the time, and went to CBS TV to show the audience the automatic speech recognition system he built. Subsequently, many companies poached him with high salaries, which made him leave academia completely and enter industry. But to be fair, the automatic speech recognition system at that time was far from practical, and it was completely incomparable to today. However, this incident at least proves that language models do work. Another thing that happened in the 1990s was that one of Jelinek's subordinates, Peter Brown, used language models to achieve automatic translation between English and French. Compared with automatic speech recognition, the difficulty of machine translation is to prepare language models in two languages, and it is best to use one-to-one sentences in the two languages for training. If you train with Dickens' English novel and Hugo's French novel, they do not correspond, and the effect will naturally not be good, since the one-to-one multilingual text on the computer at that time was only the Bible, and a small number of United Nations documents. Brown's translation system did not work well. Soon after, Brown left academia altogether to become the technical head of Renaissance Technologies, a famous hedge fund, and his ability to build mathematical models to solve problems has made both the fund and himself a lot of money. At that time, Brown's work did not receive much attention from the academic community. It was not until more than 10 years later, when German scientist Franz Ocko solved the machine translation problem better with a similar method at Google, that Brown's original paper became one of the most cited papers in that field. Of course, Ocko also used tens of thousands of times more data than other research institutions at the time, and millions of times more data than Brown. However, that's for later talk. Stage 2. Back to the language model. After entering the 1990s, people found that simply adding training data was not very effective. Ulinek did a statistic himself and found that no matter how much data was added, there would be a large number of linguistic phenomena that could not be covered. Therefore, people began to consider building language models with deeper knowledge and information in the language. The development of language models has thus entered the second stage. It was in that context that I did my language model research. At that time, we used the grammatical and semantic information in the language to greatly improve the capabilities of the language model without increasing the amount of data. For example, the likelihood of words with similar pronunciations in different topics varies greatly. For example, there are more than 40 words that have the same pronunciation as fact without tone. In the past, it was difficult to determine which one it was. But after adding grammatical and semantic information, we know that words like current affairs, fact and inaccurate will often appear in current affairs news, while words like rec, historical facts and poetry, history will often appear in articles on historical topics. Many times, once the topic is determined, you know what words to use. When the language model adds grammatical and semantic information, the training of the language model and the use of it to calculate probabilities are no longer simple statistics. Prior to this, the language model had a slight background in probability theory and statistics, and people who had taken a natural language processing course could basically build it. But the language model after that, the formula is very complicated, and most people can't understand it. Of course, after adding more information, such as grammatical information and semantic information, to the language model, the bigger challenge people face is that the computational load of training the model becomes particularly large. Regarding the amount of computation required to train the model, we will talk about it later. Here is a small example. Before him, there was a scientist at IBM who was the first person in the world to successfully train a language model using semantic information. His main job was not to improve algorithms or mathematical models, but to write a program that could use all the idle servers in IBM Watson Lab, and then compute for a year to complete the training of the model. You know, Watson Lab is a large research institution with thousands of scientists. Such a large research institution, so many servers. In your spare time to calculate for a year, you think about how much computing is. Because of Moore's law, which is that the performance of computer processors doubles every 18 months, we have the ability to perform more and more complex calculations, to process more and more data, and to utilize and store more information. However, this increase in computational volume exceeds the increase in computational power. For example, in 2012, when we did machine question answering at Google, we needed to do in-depth grammatical analysis of tens of billions of sentences, and extract all kinds of useful information, rather than simply doing statistics. This amount of calculation, even Google feels very difficult. Today, ChatGPT's language model utilizes richer language information and requires more computation. Even with a large number of GPS with stronger computing power, the computing cost is also high. In addition to mining more information in the language, since the 1990s, scientists have also proposed the language model of self-adaptation. That is, in the process of using a language model, the information entered by a person and the feedback provided indirectly can be used to improve the language model. For example, we use a language model to build opinion input method. When the user inputs Chinese continuously, the Chinese text he inputs is used as training data. In this way, the more you use this input method software, the smarter you will be. Of course, this approach requires not only personal data, but also a lot of storage space. Because at this time, the language model used by different people is already different. Today's chat actually has this function, which will continuously iteratively optimize based on user input. If you use it to write a few articles, and then constantly modify those articles, it will learn your writing habits and then output content according to your writing habits. However, if people deliberately mislead it and enter spam, the quality of the text it outputs will also decline. As mentioned earlier, mining deeper information in language can effectively improve the ability of language models. But at the same time, it also makes the amount of computation huge. Therefore, in order to make computers work more efficiently, after 2000, a lot of language model research work turned to improving algorithm efficiency. For example, in the latter part of my PhD work, I spent more than a year improving the training method, reducing the computation by 2 or 3 orders of magnitude. That is, only 1,000 to 1% of the previous computing resources are needed to do the same thing. Stage 3. Around 2010, Google developed the Google Brain, a deep learning tool. On the one hand, it can use computing resources more efficiently, which makes the language model bigger and bigger. On the other hand, it also makes the probabilities calculated by the model more and more accurate. The development of language models has thus entered the third stage. In the following years, one thing Google did was to retrain the previous language model. Without increasing the training data, the accuracy of the model improved a lot, and the quality of the corresponding product also improved, due to the increase in the amount of data and the improvement of the accuracy of language models. By the second decade of this century, computers have gradually achieved from writing a sentence to writing a complete paragraph. Before this, whether it is automatic speech recognition or machine translation, you need to give it a complete sentence and let it produce a sentence with the same amount of information. For example, you give it a Chinese sentence, it produces the corresponding English. Or you give it a sentence speech, it produces the corresponding text. The input and output is 1-to-1. And once the language model is strong enough, you give it a little input, and it can produce a lot of output. For example, if you ask it a question, it may only be one sentence, and the answer it generates may be a long paragraph of text. You give it a few keywords and ask it to generate a resume, and it may generate a page of content for you. Understand the principles of information theory. Colleagues will certainly know that the amount of input information is small, the amount of output information is large. The difference between the middle must have a way to make up for it, otherwise the content of the output will be full of uncertainty. Where does the supplementary information come from? In fact, it all exists in the language model, and information needs to be input into the language model first. The language model at this time is called production. The G in GPT stands for generative. For example, GPT-3's training data includes hundreds of thousands of books and almost all of Wikilingo's content. This amount of data is less than 1/5 of the data it uses. In fact, Wikilingo alone can answer almost every meaningful question asked by most people today. Therefore, it is not surprising that Chat performs better than many people, because a person may not learn even 1/1000th of its content in a lifetime. Of course, information alone was not enough. In order to ensure the coherence of each sentence in a paragraph of text, a language model was also needed to be able to calculate the probability of several sentences appearing together. Calculating at the paragraph level was thousands of times more computational than calculating at the sentence level, rather than several times tens of times. At the same time, in order to make the paragraphs generated by the language model less divergent, some templates are usually used to restrict the generated text. This is also why Chat can write reports and resumes well, but writing unrestricted articles is very boring. Similarly, today's writing software is usually only able to cope with the writing requirements of a routine, such as writing financial reports, writing college application materials, etc. The so-called routine is actually the template used by the computer. Today, it is generally believed in the US writer community that Chat can only write according to a certain template. Of course, in order for Chat to answer good questions or have conversations with people, it also needs to understand people's problems. This is easier than writing itself. Today, computers can do more accurate grammatical analysis of natural language than humans. Through the grammatical structure of a sentence, it can understand the meaning of common content words, namely nouns, verbs, and adjectives. Generally speaking, the meaning of a sentence is the superposition of the meanings of these words, so it can understand the meaning of a sentence. Of course, in rich human language, there are often exceptions, that is, you understand all the words in a sentence, but you don't understand the sentence. In this case, the computer has no way. At this time, it will answer randomly, or even give the exact opposite answer. Next section preview. Okay, that's all for now. The algorithms of language models can not only handle problems related to natural language, but theoretically, using other data to build similar models can handle a large number of problems that originally needed to be solved using human intelligence.